All right. So I posted the next Excel assignment. It's not due for a while. I think it's the 19th, because what we've done after today, well, last class and today, you can do question 1. We will cover everything. And the other 2 questions, 2 and 3, they all have parts. It'll be using the same formulas that we looked at in Excel and same functions, but it's going to be on this idea of confidence intervals, which we won't talk about probably until Wednesday and Friday of next week, maybe a little bit on Monday. So you get an early start on it. You can get through that entire part of problem 1. You'll have that Connect assignment that's due next Wednesday, so I would kind of focus on that for right now. But if you're looking to get ahead, get that first question on the Excel answer, because it's stuff that we've done this week. Right? Also, there wasn't an online quiz on Monday, but there will be one today. So I'll get one posted right after class, okay? It'll be due before class on Friday. All right. So we left off last class with these examples of, what's the probability we see above or below a specific value, right? For some normally distributed variable. So the process was we could turn that into a z-score, look that up in the table and find the area to the left. Depending on what exactly we wanted, we might have a little bit of work to do after that. If we want the probability that's greater than that, 1 minus the probability we find from the table. Today we're going to talk about basically working in reverse. Okay, so it's this idea that we took that equation, that formula we were using to find a z-score, where we knew the cutoff value for x and we were converting that into a z-score. Well, if we rearrange this equation a little bit, if I don't know the cutoff score that I want, but I know that I want it to be the score that gives me a certain probability of seeing that or anything below it, I can actually use this inverse formula to find that. So I'll always know the mean and the standard deviation of my normal distribution. It's just now I'm going to have to find this z-score. Okay? So we'll kind of put some numbers to this now. I'll walk you through this, and hopefully we'll see how this is really exactly what we're doing, just in reverse. Right? So let's say we have this random variable x, which is normally distributed, has a mean of 72 and a variance of 64. So let me make sure everybody's in here. Okay. I got this recorded. All right. It's like did I turn the oven off thing? I always worry that I didn't hit record. So we've got the mean is 72, the variance is 64. What's the lowest score that would be in the top 10%? Or said differently, what's the cutoff for that top 10%? Right? Well, we think about this. So I've got this variable x. I know it's normally distributed with a variance of 72, and my variance, with a mean of 72, and if my variance was 64, my standard deviation would just be, the square root of that, or 8, okay? So now what I said was, well, what's the score that would give me the cutoff for the top 10%, right? Well, the top 10% is saying that what score for x would there be the probability that I saw a score higher than that be 0.1, right? Or 10% or higher than that. Well, I know that I can convert any normal distribution into a standard normal distribution or kind of z-scores. So what I'm going to say is there's some z-score that would give me that 0.1 in that upper right tail, right? I don't know what it is yet, but I know that it exists. Now, if there's 0.1 to the right, I know there would be 0.9 to the left, which I always need the area to the left because when I go to that standard normal table, remember, the probabilities in that table represent kind of the areas to the left of different z-scores, okay? So I'm going to look up that probability of 0.9 and find the corresponding z-score that gives me that area of 0.9 in the tail, right? Or the probability of what z-score is the probability of seeing that or anything below it, 0.9. Okay? So last class, we were looking up certain z-scores and finding the probability we saw that z-score less. Well, now we don't have a z-score, we have the probability. So all these values in the middle here are probabilities. What's the probability that we wanted? 0.9, right? So I look in here and I say, okay, where is the value that's closest to 0.9? Keep scrolling. Okay, looks like it's around here. Okay, so I can't get exactly 0.9, but I can get really close, right? So the z-score that would give me that area of 0.9 in the left tail is in between 1.28 and 1.29, okay? So I looked up that area of 0.9. I couldn't find it exactly, but I know that it's in between these two values. So the z-score that would give me either one of these values in that lower left tail is 1.28 and 1.29. So anytime we're in between two values there, I'll take the higher of the two, so 1.29, every time. And if they're negative, so let's say it was negative 1.28 and negative 1.29, it's like the higher absolute value. I'll take negative 1.29 there, right? Greater in magnitude is another way of saying that. So I just looked up that area of 0.9, and approximately the z-score that would give me that is that 1.29, okay? Well, now that I have that 1.29, I've got my mean, my standard deviation, and that z-score. We go to that inverse transformation formula, and we got everything we need to plug it in here, right? Plug in that mean of 72, that standard deviation of 8, and our z-score of 1.29, okay? Any questions on that before we keep moving? I'll show you a different way of doing this as well. So another way you could have done this is once you find that z-score, I'm going to run out of room if I don't do this. I got to erase. I'm going to erase this real quick. So this is our formula for the z-score. Well, I just found that z-score was 1.29. I know my mean was 72. And my standard deviation is 8. Now I can just rearrange, do some algebra, and solve for x here. So I can plug the values into my z formula and then rearrange, do some algebra. Or I could rearrange that equation ahead of time and have this inverse transformation equation, right? So whichever way is easier for you to kind of think about, you can use that way. All right?
So when we look at those decimal points, those are the probabilities and not like the z-score?
Yeah, it's a good question. Okay. Let me think how I want to do this. I'll give you a visual and then I'll show you on this table. So let's say I chose, and this is going to be a weird one, but I know that it's in the table, so hold on. So here's my standard normal distribution, right? Let's say that, it's 1 point, I think it's, let's say I know the z-score, right? I can look that z-score up and find the area in this lower left tail, okay? If I do that, I'll find 0.025, right? So let's say I go here, I look up negative 1.96, so negative 1.9 is here, 0.06, so negative 1.96. The area to the left of that is 0.025. Now I could have instead said, if I want the area of 0.025 in the tail, what's that z-score? Well, now I have the probability, so now instead of using the row, instead of using the row and column headings, right? Well, I'm not using a z-score, I have a probability now. So now I look up in the middle, that probability I have of 0.025. So then I find that, and the z-score that corresponds to that area in the tail is negative 1.96.
So like, let's say it's not exact, how would you like us to like go about that?
So when it's not exact, just like we did, well, I have one more example, and it'll cover, yeah.
Let's go back real quick. When it's, you said when it's negative, you check the opposite one. So if it's like negative 1.1 and negative 1.2, you use negative 1.2.
Yep. Yeah, and actually both of those questions we'll hit in this, we'll hit in this next example. So example number 2. Okay. Let's say I have the same sort of setup, but now I want the cutoff for the bottom 40%. okay? So the bottom 40%, right? So I'm going to leave this Z distribution down here because we'll use it. But now I'm looking at that test score variable X. It's got a mean of 72, standard deviation of 8. Now I want the cutoff. That gives me an area of 0.4 below it or 40% below it, right? Well, first of all, what do I know that this cutoff score has to be less than? 72. The area to the left of it is less than 0.4, and that's because we know the area to the left of the mean is 0.5. So right away, I know when I find my final answer, it should be less than 72, right? Because 72 would be the cutoff for the 50th percentile. So I know that this cutoff score would correspond to some Z value that would give me an area of 0.4 to the left, or 0.4 in that lower left tail. Or the probability that I saw that Z score something lower was 0.4. All different ways of saying the same thing. So I'll look up 0.4 in my table. So here, if I find what's close to 0.4, so your question earlier, what if I can't find exactly 0.4? Well, I'm in between these two. So I just find the two values that I'm in between that are closest to the probability I want. So 0.4, the closest I can get is one of these values, okay? Now, I could look here and say it's a little bit closer to this one than over here, but for the sake, just for simplicity to make sure we're always doing the same thing, like I said, you're in between two values, I'm just gonna treat it as though choose the highest of the two, the highest in magnitude. So here we're in between these two, that's negative 0.2, scroll up, negative 0.25 and negative 0.26, so we'll use negative 0.26, okay?
You choose the value, the higher absolute value.
Yep, yeah, value of the higher absolute value, higher in magnitude, or honestly, because the way this is set up, you always choose the value that's to the right. That's another way you could think of it, yeah.
So, like, are you supposed to like memorize this or?
Memorize this table?
Yeah.
No, you do not have to memorize this table.
Like in general, like if I wanted to have like a major in physics statistics.
No. So one of the things I might have went through it really fast last class, right? I can recreate this table in Excel. I'm always going to have this table available to me. And in fact, we'll get to Excel in just a second. I've got some formulas I can use in Excel that will always be able to do this for me. Yeah, there's no way you'll have to do this every single time. Or you'll have to like memorize or come up with this number yourself. Right? So where do we leave off, right? We had negative 0.26 was that Z score. So we found this guy. And now it's just a matter of plugging values in. We have that inverse transformation formula, which was, I think the way I had it set up was Z times the standard deviation. 72, well, plus negative 0.26 would be minus 0.26, and then times that standard deviation of 8. If I do that, I get like 79.2 or something, or let's look at the exact, I forget the exact value. Got it in the slides here, there's no sense in guessing. Well, 69.92, right? Now, if we think about this, what did we say first off? Yeah, I knew it had to be to the left of 72. Oh, sorry. We know that it had to be less than 72. So right away when we look at this, we could have ruled out B. If we're looking at test scores, A doesn't make a lot of sense. And what would a test score of 0.26 likely be the cutoff for? 10% be generous. I would say like 1%, right? I mean, it's going to be very, very close to the end, right? So none of these answers really make a lot of sense for the context of what we're doing, given that we know we want the bottom 40%. I probably could have guessed D there and been okay. But we actually went through, looked up that Z-score. Now here I showed you, if you plugged it into the Z-score equation, you could have then rearranged it yourself, or you could have started out with that inverse transformation, plugged everything in. Now, instead of writing 8 in here, I wrote in the square root of 64, because remember, originally, I was given the variance, right? So if I want to find the standard deviation first and then just keep using that, that's fine. Or I could think about it as whenever I see that standard deviation, I need to plug in the square root of the variance, Okay? Just trying to give you different ways of looking at all this. Any questions there before we keep going? All right. So let's go back to this Excel. There's this inverse transformation sheet. I'm going to delete this real quick so I can build it again for you. Let's say we have this exact same examples. Mean of 72, variance of 64, right? And in fact, I'm going to put this up here just to show you something here in just a second. So if I want the X value that gives me that area in the tail, or the probability of seeing that cutoff score or anything below it is 0.9, I know the area in my tail. I want to find what that X value is, that cutoff score, right? Now, the way that I just showed you, we first have to find the Z-score, then plug that into the inverse transformation formula. So if I wanted to do that, norm.s.inv, what this is going to say is I'm using the standard normal distribution, so those Z-scores, and I know the area that I want to the left of my Z-score is that 0.9, right? So that's all I have to tell Excel. And what Excel does when it sees this is essentially it looks up that area of 0.9 in the table and then goes over and up to find what Z-score would give you that area and then spits back out at you what that Z-score would be. Now, the nice thing about Excel is we're not in between two values. We're not limited to 2 decimal points. So it tells me exactly 1.281, right? Now that I have that Z-score, I just use that Excel as a calculator to take the mean, add to that my Z-score times my standard deviation. If I only have the variance here, I can use the square root of the variance to represent my standard deviation. Okay? So I could do it this way, and I get 82.25. Now notice, that's really close. Oh, where is it there? There we go. Nope, that's not it. Really close to the answer we found by doing it by hand, but it's a little bit off because we didn't have to round those intermediate values to 2 decimals, right? So we can be a little bit more precise in Excel. Now, you might, in certain situations, wonder what that Z-score is, but ultimately, the final step, the question we originally started out with was, what's that cutoff score that gives me that area in the tail? So if you don't really care about what that Z-score is and you want Excel to do everything behind the scenes for you and just spit out at you this 82.25, I can use the norm.inv function, tell it the area I want to the left of that cutoff score, which is, I'm going to use a cell reference here for a second, 0.9, right? It's that 0.9, comma, tell it the mean, tell it my standard deviation, so the square root of my variance. And now what Excel will do is, because it's not norm.s.inv, it says, okay, take this area, find what Z-score would give me this area to the left, right? Or the probability of seeing that Z-score or anything below it is that probability I'm telling you. Then use this mean and this standard deviation, and the Z-score that you find, throw that into the inverse transformation formula and spit back out at me the answer, right? So it does like all the steps behind the scenes for you. Kind of like when we went from norm.s.dist to norm.dist, okay? So same exact value, right? Just kind of cuts out the middle steps there. Now the nice thing about using this as a cell reference is, let's say I now want to find the cutoff for the bottom 40%, which was that second example. Change this to 0.4. Sure enough, we get 69.97, which once again, going to be very, very close to what we found, but a little bit different because we're not constrained to 2 decimals, okay? Any questions over anything I did here in Excel, or we're okay with this? Double check the chat. All right. Okay. So that kind of gets us there. And I'll replace the Excel formula that's on Canvas with this one that we've been working through in class, because I know that we did a couple things that were a little bit, weren't in the original file, weren't not necessarily you have to have them, but just a little bit of additional work, okay? All right, and I think I'll do this example next class, or maybe if we have time for it in the class today. But we're gonna skip ahead a little bit, not skip ahead, we're going to take a slight divergence from what we've been talking about to set up what we're going to do on Friday, which is talk about distributions of sample means, okay? So everything that we've been doing, I guess I should go back here. Everything we've been doing, remember, this represents the population mean, this represents the population variance. Well, most of the time, we don't have population data, right? We have sample data, okay? So we want to start thinking about how do we make sure we have a sample that's reflective of the population as a whole, okay? So we'll talk about some issues that might exist. Now, for us, I'm going to gloss over this. Every example we'll look at, we'll be thinking about a finite population. There are infinite populations. Usually that's if you have some data generating process that really could just kind of continue on in time indefinitely. But we're always going to be dealing with a finite population. So even if it's the entire US, right, 300 and some odd million people, there is a finite number where it stops, right? You know, we talked at the very first week how it's not feasible to always take a census. We usually can't get population data. It's expensive or just not feasible. And so we're going to have to be dealing with sample data to make inferences about the population. All right? So this is kind of the setup. Just a reminder, you know, population sample size, the population size is capital N. Our sample size, we're going to denote as lowercase n, right? So that's not too bad. It's all kind of review. So when we build this sample of size lowercase n, we can do it with or without replacement. So with replacement would be like if I had a hat in front of me and I was randomly drawing 5 people in this section's names out of the hat, had everyone's name written down on a single piece of paper. I reach in, pull out a name, and let's say I record that person's height. I write it down in my sample data set. Put the name back in the hat, shuffle it, redraw a name, write that person's name and height down, put their name back. Right? I could keep putting their name back in the hat before I draw the next time. Without replacement would just be if I choose a name, record that height, throw it away. Don't put it back in the hat for when I go to draw that second sample. Now, which of these do you think is probably preferred? I think it's in the slides, but just from describing that process, why would I want to maybe use without replacement more often? What could happen with replacement? If I'm putting the name back in the hat, I could get the same person. Well, now my sample has one person who has twice the weight, right? They count for 2 observations, where everybody else in my sample is only going to count once, right? I mean, in a really strange turn of events, out of 40 people, if I drew, you know, a sample of size 5, if I end up drawing the same name 5 times, well, that's not a great sample, right? I've got the one person represented 5 times. So more often than not, we're going to want to use without replacement, okay? The other 2 things we want to make sure, you know, I'll never use an example where this isn't true, but just to kind of cover our bases, each element or observation that we have in our sample should come from the population. If I'm interested in the average US income, nobody in my sample should be from Canada, right? The elements should be selected independently. So just because I get someone to respond to my survey, I shouldn't ask if they have any siblings who also want to respond, right? Because that would make those not independent, right? Because for me to get the siblings, I had to first get the response from the person or the other sibling. But we'll always have examples where these are true. Okay? I'm going to talk through 2 very closely related ideas of something we can do to make sure our samples match up with the population. So the first is going to be stratified random sampling. Okay? So with stratified random sampling, I'm going to divide my population into non-overlapping groups. Okay? So for the sake of this example, we won't get into the kind of the sociology of this. Let's assume that I'm interested in the average height in the US. Right? We'll assume that we have kind of males and females as our 2 strata, our 2 groups. Well, let's say I had a sample of size 20, I randomly select 20 people, and I end up with 15 females, and I end up with 5 males, right? Well, I know that's an issue because that sample doesn't match up with the population, which is about a 50-50 breakdown, right? 50% male, 50% female. So if I'm interested in height, I might want to make sure my sample matches up with the population. So what I could do is divide this into 2 groups. From each group or stratum, randomly select 10 females, randomly select 10 males, then throw those 2 random samples together to get my full sample. Now I have a random sample, but I've done something to ensure that the breakdown of that sample looks like the breakdown of gender in the population. Right? And it doesn't have to just be with gender. We can think about age Age, right? I might want to make sure the age distribution of my sample looks similar to the age distribution of the population. The income kind of breakdown within my sample looks similar to the income breakdown for my population of the US, right? Really anything I'm interested in. Well, sorry, anything that I think might impact the variable that I'm interested in, right? Yeah, if I want to make sure, you know, if I know that about 30% of people have a college degree, then maybe I randomly select 3 people from the group of people with college degrees, 7 without a college degree, put those together, get a sample size of 10. Yeah, it's really when you want to use this is when you have a variable that you think is directly related to the variable that you're interested in. So that's why I use gender height. Like I said, it's not a perfect example because it's, you know, completely binary, but like it gives a really good idea of like, we know that this variable of gender is going to be related to the variable of height that we're interested in. Okay, so very similar idea would be cluster random sampling. And I'm never going to expect you to like identify the difference between these two, but it's basically the same thing, but instead of dividing, like randomly sampling from different groups based off of a characteristic, you're just randomly sampling different subpopulations. So usually it's like geographic. So what I was thinking of, the example I like for this is, if I'm interested in something about maybe like lung health in big cities, in cities over 1 million, well, instead of randomly sampling like, and maybe ending up with more people from Philly than from New York, I might then look at taking randomly sample 10 people from each big city over 1 million, and then throw all those together to get my full sample, right? That way I make sure every city is represented equally. And you know, I can't have people coming from Philly and from New York, right? Those are kind of distinct subpopulations. But each one of those cities kind of just looks like a smaller scale version of every big city, right? So that's kind of the idea of cluster random sampling. It's not based off of another characteristic, but we're just looking at several different like small subpopulations that look like small scale versions of the population, right? But we're making sure that each one of those kind of subpopulations is represented. You could think about kind of in political polling, the way that this might look is you have different regions of the country. So like if I randomly sample 20 people and they all end up being from the South, well, I know the South predominantly leans more towards the right than the left, so my sample won't match up with the entire population. If I break it down into different regions of my country, so I've got a couple, you know, certain number of states in the Midwest, Northeast, West, maybe even break it up into like Southwest and Southeast. Now I randomly sample 10 people from each region, put those all together. Now I have kind of this larger sample that's still random, but make sure that each region is equally represented. Okay, any questions over that before we keep moving? I'm not gonna like do too much in terms of like having specific questions on the exam related to this, but I'm just setting us up with this idea of we wanna make sure our sample looks as close to the population as we can, okay? Without like hand-picking people, right? We're still making it random. So it's hard to get population data, so we have to use this sample. So what could go wrong? So we'll use this example to set up 2 different biases that could exist even if we randomly sample, right? So 1936, presidential election. Alf Landon lost to FDR. Great name. You know, they sent out this literary digest poll, which is like this little book. My grandma used to get it. It was almost like a little magazine. But in 1936, prior to the election, they sent out 10 million survey cards. So their idea was, we're going to get a pulse for the United States and be able to predict the election. Right? 2.5 million are sent back. That is a big sample, right? 2.5 million people is a lot. So these 2.5 million surveys about who people were going to vote for in the upcoming election predicted the popular vote was going to go towards Landon, and the Electoral College is going to be a pretty big win as well, right? Well, obviously we know that didn't happen. Not only did FDR win, he won like almost every electoral vote, right? And so how did this poll, how did this survey, this sample get it so wrong? They were so far off of what the population was, right? Or the population mean of who people were going to vote for. So let's think about how they actually sent these surveys out. So these 2 were stupid, right? Did they make math errors? Did they use like the wrong formula? Population says sample variance? No. But did they only mail these surveys to Republicans? Because if you only mailed them to Republicans, and that was kind of Alf Landon, then it's going to look like Alf Landon's going to win. If Republicans were just more likely to respond, then your sample is going to make it look like you win. So for let's say I send out 10 million. Let's say I make sure that I send 5 million Republicans, 5 million to Democrats. Well, if 0 Democrats respond and 2.5 million Republicans respond, now I've got a sample that doesn't match up with the United States, right? Because on average, we know that the U.S. breakdown is about 50-50 in terms of political party leanings, right? So what these two things are really describing, this first one, if I only send it to Republicans, would be this selection bias. I'm over-selecting, I'm systematically selecting from a certain group within the sample. I'm over-selecting Republicans, right? That's a selection bias. The non-response bias would be that if Republicans were just more likely to respond to this survey, now I have a non-response bias. It's gonna lead to me having more Republicans in my sample than what is accurately representing the population, okay? So these are our two biases, right? We'll talk about in the context of this example how that looks. So what the Literary Digest did was they got their list of names of people to send this survey to from cross-listing telephone books and car registrations. Who owned a telephone book? Who owned a telephone and a car in 1936? Really wealthy people. If we look at a lot of the data, wealthier individuals tend to lean more towards voting Republican, okay? So they built into their list of people to send these surveys to a selection bias. They're gonna be over-selecting wealthier people who tend to vote more Republican than kind of non-wealthy people, right? So there was this paper that went back out and tried to survey people from this time frame and ask them who they actually voted for as opposed to just kind of what their response was. So that what they found was for people who own cars and telephones, right? Landon would have won about 53% of their vote. So their kind of prediction of 57 wasn't too far off, right? So these are people who actually voted for not just their response to the survey, but actually voted in the election for Roosevelt and Landon. Now, people who only owned a car, right, not both, in the election, only 37% of them voted for Landon. So even if they would have just used car registrations, the prediction of this poll would have been a lot more accurate, right? People who only own telephones, same kind of idea, 37%, only 37% voted for Landon. And then neither here we can see 73% of those people voted for Roosevelt. So it's this idea that because they used to build their list that they had to own both a car and a telephone, they ended up with a result that didn't look like what the population mean was, right? Or what the population would have kind of resulted in, okay? The non-response bias, right, was this idea that maybe Republicans were more likely to respond. And I can't remember all the exact details of this paper because this was an actual paper that went back through and tried to kind of poll these people who voted in the 1936 election. But it doesn't matter what category we look at. If they own both a car and telephone, only a car, only a telephone, or neither, notice, of people who voted for Landon, what percent were likely to kind of send back any type of a response to a survey that was sent to them? Well, the people voting for Landon here, 35% compared to the 17% of people who were likely to respond to a survey who voted for Roosevelt. So we had a huge non-response bias, right? The Republicans, or people who voted for Landon, were twice as likely to respond to these surveys. Okay? And that is kind of our non-response bias. Okay? So what else could have gone wrong? Or not just in the context of this example, because the selection and the non-response bias exist in any data collection. Well, people might lie to you if you're collecting data, either on purpose or not, like maliciously or non-maliciously. So this idea of maliciously lying could be like, I ask you what your income is, and you tell me $300,000 when you're making like minimum wage. Yeah.
When was this sent out?
This survey?
Yeah.
Oh, this is the 1936.
Was it before, like how close before the election?
Oh, so I don't know the exact date. I'd have to go back and look at it.
People change their mind.
Yeah, so that, you're already thinking about the context of that example for this. Non-malicious lying would be like, you ask me who I'm voting for, I tell you someone, but I change my mind before election day. Well, I told you the truth. It's just that now you have data that, because it changed, the data is now wrong, right? So you could have people non-maliciously lying as well, right? Or malicious lying. So if I asked you what your income was, the idea is maybe I'm making $20,000 a year, but I tell you I'm making 300. That's a malicious lie. Maybe I'm making exactly $21,324 a year. I tell you I'm making 22,000. I'm not giving you a perfect, the exact amount. I'm not maliciously lying to you. I'm just kind of rounding in my head, right? So these are some of the things that can go wrong as well. And then kind of the final one, there's a lot more research on this in psychology, and just the phrasing of questions can elicit different responses. So there was this example I saw, I want to say it was like a poll that was done on Fox News, where they asked 2 different questions, but it was really the same thing, just phrased differently. And they got responses that were about, it was like, are you, basically favorability ratings of how Trump was doing. And they were off by 10%, just by phrasing the question a little bit differently. So how we ask the question and whether or not the question is understood may also elicit different responses. So we'll work through a couple of examples just to kind of hammer home down some of these biases that we're thinking about. So let's say I asked everybody in this class how they would rate their health from 1 to 4, right? And then look at the results. Oops. So let's think about these different types of biases. So my selection bias, if I'm asking everyone in this class, and I'm thinking about my population as the United States, I have an over selection of young individuals. What's probably true about younger individuals' health relative to the entire population? Probably a little bit better, right? There's 80-year-olds in the population, right? So your health is automatically, I'm over selecting from a certain age group. My non-response bias, if I didn't require you to respond, what do you think might be the non-response bias here? People who are healthy, right? Well, I don't know, at least for me, I don't see why they wouldn't respond. People who are unhealthy might not want to let me know they feel like they're an unhealthy individual and might be less likely to respond. And maybe people that are healthy are more likely to respond because they want you to know that they feel more healthy. And so both those things are going to result in me having a sample with healthier individuals and not as many unhealthy, right? So I've got a non-response bias that could occur here as well. Now, typically what I do if I have kind of a normal semester is I use this kind of eye clickers, or like maybe like if this was an online quiz question, why would that help with a selection bias? If I was giving you points for responding to this, yeah, I'm going to create an incentive so that, right, and that's what all these other places do. You ever gotten all these emails? I get them all the time. Take this survey for a chance to win a $25 gift card, right? What they're trying to do is reduce this non-response bias, creating incentives that everybody likes. Everybody likes $25, right? But now the problem is, even with that incentive might work for individuals that don't have kind of lower incomes, but it might not be a good incentive for people with high. So now I've even created a selection bias by trying to resolve my non-response bias. So it gets kind of tough, right? You could have just misunderstood the question, right? I could have looked at this real quick and said, oh, I feel like I'm a 4. Well, no, higher number, that's the best health. Well, no. The way that this was set up was 4 is the worst, right? You could have also maybe just, I don't know, I feel like a 1.5, so I can't tell you the truth. You forced me to be one of these possible options, so I'm going to tell you a 1 or a 2, but that's not completely accurate, right? I'm not maliciously lying to you, but I have to give you one of these values. So all those biases kind of exist in here. We kind of talked through some of them. I just want to kind of give you more examples of thinking about these. So the other one I always use is, how many alcoholic drinks do you have on average each week? Let's think about the selection bias, pretty similar to the health one, right? If I'm asking a group of college-age individuals how much they drink, what do you think that mean is relative to the population? Probably a little bit higher, right? I say a little bit, that's probably being kind, right? So now the non-response bias here, how could I maybe have created a non-response bias in here? If I'm able to observe your response next to your name, yeah, if people aren't 21, well, it's not that they might lie and say 0, but they also might just not respond, right? Or maybe if I'm drinking at an amount that I think Professor Lance is going to judge me about, I might not respond either, right? Or I might lie to you there, right? So the non-response and lying kind of go hand in hand, because a lot of the incentives that would exist to not respond would also exist for that individual to lie, right? which either way is a problem, because if they lie, they're usually going to lie in one direction. And if they don't respond, that also one less data point that would have pulled me up in the other direction. So kind of all those things exist as well. Also, even if this happens a lot with the survey data, if you ask somebody about something that happened the past week or on average, they're going to give you a value, but like who's tracking exactly the number of drink, right? And who, I'm going to give you the best, like kind of even with income. I don't know exactly to the cent what I made last year. I can give you a number that's close, right? And I'm not trying to lie to you, but you know, I'm going to be a little bit off. All right, where are we at? Oh, okay, cool. So I want to work through this, and I'll post something up on Canvas. It's an article that looked at this, and I'm not going to go through every one of these points like in depth today, but I do want to kind of point out, I think it's interesting. If we think about the last election, right? So all these polls, all these surveys got it wrong. Almost all of them predicted that Clinton was going to win the last election, and people were like trying to figure this out, right? So there could be some selection bias that exists in political polling depending on where it's done. Excuse me, I kind of think about this as, you know, if I'm doing this in different areas of the country, rural versus urban, maybe there's some issues there. I think most polling, they can take care of these selection bias issues. They can try to use stratified random sampling and try to ensure that they're not having this selection bias. But what they can't quite do is, especially when undecided is a potential answer, right? There's probably just a lot of people who, if I call them and ask them who they're going to vote for, they might just tell me undecided, even if in the back of their mind, they kind of know who they want to vote for, right? And I think they did some like exit polling, or they had some survey data in this paper that I'll post that showed that the non-response bias, or this kind of indication of undecided, was higher from people who ended up voting for Trump when they looked at like what do they call them, exit poll data, versus people who voted for Clinton, right? More so, and I'll come back to this in a second, this article brands them shy Trumpers, which were people who either were responding as undecided or maliciously lying and saying they weren't going to vote for Trump, even though they knew they were, because of maybe they felt some type of like social pressure that didn't want to like make it known they're voting for this guy, right? And so something I think, you know, we can think about when we're doing surveys and polling, especially with political polling, I would think, is you want to try to take away any type of disincentives for someone to respond what their actual truthful response is. And you know, when you have face-to-face, like there's a person in front of you, if you're at all way concerned what they're going to think about your response, right? And I think it makes a lot of sense in the context of like someone telling you they're going to vote for Trump. I mean, I go on Twitter, it's a mess, right? And so one thing that you can think about is, well, how can we fix this? Well, we can do polling things online and have complete anonymity, right? You never have to look at another person in the face. And so people from these online polls might be a little bit more likely to give you an accurate response as opposed to like these call banks. I did one when I was in college for some local politics in Lafayette, and I just called people and asked them who they're voting for. And I got a lot of people that were mad, but no, it's just, you know, they'll tell you, but you know, there is another voice, even with a phone call, there's another voice on the other end. You know, someone like has your name and is going to know how you respond. So, you know, I thought the article is interesting. It's a little bit more in depth than I'm even making it here. So I'll put that up on Canvas if anybody's interested. Also, just unintended lying. You kind of said it earlier with the Alf Landon, right? Maybe they weren't, you know, responded one way in the poll, but changed their mind upon election day. Depends on how far in advance those polls were taken, right? So I thought that was kind of an interesting application of talking about some of these different biases. So we'll start with sample mean distributions next class, and I'll end with this meme that I always kind of get a chuckle out of. So hopefully you find it as funny as I do. So, so if hotness was a normal distribution, you'd be 3 standard deviations above the mean. I would say to try this and say, you would be a z-score of 3. If they don't know what that means, then like they're dumb and just walk away. No one likes that. Okay. Anyways, so we'll leave it there. I'll get an online quiz posted after class today. 2 short questions, getting some practice using that standard normal or that z-table, and then we'll jump into what the distribution of sample means looks like on Friday. Okay? All right. We'll see you guys Friday.